In the summer of 1962, NASA committed to the Lunar Orbit Rendezvous mission profile. This architecture allowed the agency to bypass a massive, unbuilt rocket by utilizing a lightweight lander to reach the surface, while a command module waited in orbit. Reaching the moon required an engineering compromise that introduced a definitive single point of failure. The lunar module was split into a descent stage for landing and an ascent stage for the return trip. If the ascent propulsion system failed to ignite and sustain thrust from the lunar surface, the two astronauts would be permanently stranded 380,000 kilometers from Earth. To maximize reliability without the weight of redundant engines, engineers stripped away all complex ignition systems. They utilized hypergolic propellants, chemicals that ignite spontaneously upon physical contact in the combustion chamber. The system essentially featured only two moving parts, the valves controlling the flow of fuel and oxidizer. Once the crew was on the surface, each astronaut relied on a portable life support system, or PLSS, a specialized backpack providing oxygen, cooling water, and carbon dioxide scrubbing. A strict countdown governed their survival. Between the PLSS limits and the lunar module's internal batteries, the astronauts had a maximum of 48 to 75 hours before their consumables were exhausted. In the event of an engine failure, the crew would face a slow death within a rapidly dying spacecraft. Their survival was measured in hours, as the onboard lithium hydroxide reached its capacity to scrub carbon dioxide from the air. The pursuit of a lunar landing forced NASA to build a mission architecture that required absolute perfection from a single rocket engine, leaving the crew with zero physical margin for error. Internal planning documents show that NASA did explore physical rescue architectures. In December 1965, North American Aviation presented a feasibility study for a dedicated lunar rescue vehicle to retrieve a stranded crew. This diagram shows the mass budget required to convert a standard module into a lifeboat. Engineers plan to remove 188 kilograms of scientific equipment and non-essential systems. In the resulting void, they would install 200 kilograms of specialized hardware, including extra crew couches and extended life support umbilicals, to provide oxygen to the stranded crew during an orbital transfer. The proposal was mechanically sound, but it was defeated by the logistical bottleneck of the Saturn V launch vehicle. A Saturn V rocket could not be kept on a launch pad in a permanent state of readiness. The vehicle relied on volatile cryogenic propellants, liquefied gases kept at extremely low temperatures, which caused compounding thermal stress on the rocket's plumbing. Assembly inside the vehicle assembly building took months, and the rollout to the pad occurred at a maximum speed of only 1 mile per hour. This timeline compares the rescue's arrival against the crew's survival. Even an expedited emergency launch campaign required a minimum of 2 weeks for pad preparations and propellant loading. Because the astronauts on the moon would exhaust their life support in a maximum of 3 days, a rescue vehicle launched from Earth would arrive long after the crew had perished. The laws of logistics and the behavior of cryogenic fuels rendered the physical lifeboat concept operationally moot. Command Module pilot Michael Collins orbited the moon entirely alone while his crewmates were on the surface. If the ascent engine failed to ignite, Collins would be forced to execute the return burn to Earth as the mission's sole survivor. Collins carried a solo book containing 18 different rescue scenarios, though these were limited to cases where the lunar module achieved some form of orbit. This visualization shows the risk of these maneuvers. If the lander's engine underperformed, Collins would have to use his own ship's surface propulsion system to dive into a decaying orbit. This required a precise calculation of delta V, the change in velocity required to alter a spacecraft's path. If he expended too much fuel during the catch, the entire crew would lack the energy needed to return to Earth. These maneuvers relied on Clohessy-Wiltshire equations, a mathematical framework used to calculate the relative motion between two orbiting bodies. Because these equations assume near-circular orbits, they break down during an eccentric abort. A manual miscalculation by Collins during this high-stress docking phase would result in a fatal collision or mission failure. Recognizing that physical rescue was impossible, the United States government developed socio-political contingency plans to manage the fallout of a lunar catastrophe. In July 1969, speechwriter William Safire drafted a memo titled, "In Event of Moon Disaster." The document outlined a phased procedural sequence, including a presidential address emphasizing noble sacrifice. It specifically ordered NASA to terminate all radio communications with the stranded men immediately following the president's speech, granting the astronauts privacy in their final hours, while sparing the global public the trauma of hearing them succumb to hypoxia. At the moment communications were severed, a clergyman would perform a public ritual modeled on a burial at sea, commending their souls to the deep. The risk posture for Apollo acknowledged that spaceflight at the edge of technological capability carried an irreducible probability of death, a price the government accepted. Military intelligence networks rescued the Apollo 11 crew from a catastrophic environmental threat upon returning to Earth. As the capsule approached splashdown in the Pacific, an Air Force meteorologist spotted a fatal storm system developing over the recovery zone. He used data from Program 417, a classified National Reconnaissance Office satellite system used to track weather over denied territories for spy missions. The National Reconnaissance Office, or NRO, is the agency responsible for American space-based surveillance. Based on this covert intelligence, the Navy redirected the USS Hornet to new coordinates, saving the crew from a dangerous impact. The rescue paradox was finally solved during the Skylab program in 1973 by transitioning operations to low Earth orbit, or LEO, the orbital space approximately 160 to 2,000 kilometers above Earth's surface. This diagram shows the Skylab SLR rescue configuration. During an orbital crisis, engineers retrofitted a 3-person command module with 2 additional crew couches in the lower equipment bay. This allowed a 2-man rescue crew to launch and return with 3 stranded astronauts. Skylab succeeded where Apollo Lunar Rescue failed because the station functioned as a safe haven. It possessed massive internal reserves of food, water, and power, allowing a stranded crew to survive for weeks while a rescue vehicle was prepared and launched from Earth. The history of Apollo abort protocols reveals a specific paradigm in spaceflight. The capacity for rescue is dictated by the availability of time, the rarest consumable in the vacuum of space.